Thank you so much, Ron, and thank you so much to the organizers for inviting me. So indeed, I'll be talking about bias transpositions and joint work with Alan Yan. Later, after I sent the abstract and the title, I realized that some of you have seen a version of this talk, so I added a few details and a few new stuff, so hopefully everyone can see something new today. So this is a card shuffling talk, and it has to do a lot with using algebra to diagonalize transition matrices. And whenever we mention that, we need to start with regular random transpositions. So we have a deck of n cards, distinct cards. And one way to shuffle them is according to the random transposition model. Which suggests to pick two cards uniformly at random with replacement and swap them. Okay, so of course we will all agree this is not the best way to shuffle a deck of n cards. It will take quite some time, as we will see. But up to this date, this is a model that works very well when studying DNA sequences. So in biology, they care for something like this. In math, we care because this is the first time that representation theory was used to analyze a card shuffle. In fact, you know, one question that we care about is how many repeats do we need to iterate until the deck is shuffled well?
You mean?
Excuse me?
I've forgotten what with replacement means.
It means that, well, all it means is that your left hand picks a card uniformly at random. The right hand picks a card uniformly at random. It might be the same card.
Oh, okay.
That's all.
Okay.
I wrote it this way because soon we will be changing the measure according to which we are picking the cards. So this is the seminal work of Diaconis and Shahshahani. Who proved using representation theory that it takes 1/2 n log n steps to shuffle the deck. We'll get, first of all, I'll make everything rigorous very soon, but we'll also discuss their work quite extensively today. Just so that people don't start running away, I will keep it basic, linear algebra level, no representation theory, as much as I can. So hopefully, I just want to explain how we use these things in card shuffling. The model I want to talk about today.
Representation theory is linear algebra.
Thank you. Just like we don't learn it first year of undergraduate. So as we will see later on, it's a rare occasion that we can actually diagonalize transition matrices. We'll see that in a moment. So I want to talk about one other transposition problem where this magic happens, bias transpositions. So the way we do this now, this is what changes, how we pick the two cards. Let's say that, for simplicity, capital N is even, and say the top n cards are picked with probability say A over n, and the bottom n with probability B over n.
In the top half of the deck?
Yes.
Top half of the deck.
Top half. It really doesn't matter where the locations are. All I mean is half of the cards have this type of probability of getting picked, and half of them this. We'll see it later that the position doesn't matter. But it's fixed. Yeah. Yes, please.
But I want to make sure I understand it.
Yeah, please.
It's not the index of the card, it's the location of the card in the current deck that gives the probability.
Yes, it is the position. It is.
So after a card in the top of the desk has been interchanged with one in the bottom of the desk,
Excuse
of
me?
the deck,
Sorry?
if a card in the top half and the card in the bottom half have been interchanged, they also interchange probability.
Right. Bottom end with probability. Okay, and then I just want to say that, let me make sure, perhaps I want capital N here to make this work. The important thing for the result is that B is less or equal than A. Because the cutoff time, meaning the mixing time, our result says that this gets generalized to 1 over 2B and log n. So the smallest weight captures. Also, we should make sure that this A and B are fixed, like they don't change with n. So the result could quite change if we get very close to 0, if B is very close to 0. Okay, so roughly this is what I'll be talking about. And my focus is very much on the techniques. But I should also mention that this is a problem that I learned for the first time, like on a name workshop, like when I was graduating, when I was finishing my PhD. And so it was a good occasion to solve this and put some closure on this question. Okay, so let's make things rigorous and see how math comes behind card shuffling. So first of all, when we buy the deck of and cards, they all come in order. So that corresponds to, say, the identity element. And then say we were to flip the top 2 cards. That corresponds to the transposition 1, 2. So if we keep playing this game, we see that a configuration of the deck really gives a permutation. Okay, so the configuration space of these Markov chains is going to be a symmetric group. So if we take 2 permutations, we will build the transition matrix as follows. So the XY entry of the transition matrix will just give us the probability of moving from X to Y after 1 step. And since I said we need to iterate this many times, we're going to be taking powers of this matrix. So the XY entry now will be giving the probability of moving from X to Y after T steps. And what we see in this type of card shuffles, at least, is that if we let T go to infinity, this will look more and more like 1 over n factorial. And we like to study this convergence with respect to the total variation distance, just to set some notation, at least for people who already know those things. So just to make it clear that there is a probability measure behavior here, we can put the x on the index and the y here. So when we add over all y, this should add up to 1. So this is the probability measure that we want to study. And its distance from the uniform measure. So in this case, we care about 1/2 of the L1 norm. Okay. And we like to look at worst case starting scenario. So we will maximize over the starting point. Okay, so just to make it rigorous, what it means, how long till the deck is shuffled well enough, you give me an error, So we can define the mixing time to be the first time such that the total variation distance becomes less than epsilon. So this is the type of question we ask. And let's write down these two theorems. So what they proved is that for random transpositions, first of all, if we take 1/2 n log n steps plus a little bit more, but of smaller order steps, then the total variation distance is small. I'm lying here. There might be some constants that I'm throwing away, but later on I'll write something more precise. And then if you take a few less steps, then the total variation distance is very big. And to write this, we can write it this way. And now it becomes equality. Okay, the more precise statement I do want to write is part C, which is due to Lucas-Teissier. And was a wonderful result, again, using representation theory. It is that, if we look at this type of limit at time 1/2 n log n plus Cn, C now can be positive or negative, then this actually is exactly equal to the total variation distance of two Poissons. And this is called the limit profile. So, this turns out to exist as a function of C, and it's called the limit profile, and it is something that we are noticing more and more on different card shuffles or Markov chains that exhibit cutoff. But since I'm talking to many experts, I have no idea when this thing exists, actually. So if we have cutoff, when does it exist? And sometimes even if you don't have cutoff, this type of function exists. So, but this was a very nice occurrence of a limit profile, and it was a conjecture of Diaconis for many years, because apparently, if you just look at the number of fixed points of your card shuffle at time t, this is what you will get. So just the fixed points were able to give you the limit profile behavior. Okay, our theorem. Which is in progress. We are done typing some things, but we are investigating more questions of this form, is now if we take this many steps, and our window is not optimal yet, we are working on it, so if we take log n steps, then we're good, then the total variation distance, again, I'm lying about the constants. And the second part, I cannot claim we are the ones to do it, because it is really what they do for random transpositions. We just look at fixed points to say that if we take less steps, then the total variation distance is big in that sense. Okay, so this is what we call the cutoff phenomenon, by the way. So this is the usual picture where if we plot the total variation distance as a function of time, you start being equal to 1, and then very suddenly you drop, and the drop is exponential. Yes?
On higher order n in the first statement, like plus little of n or something.
Here you mean?
In the result, then d is less than e to the minus c.
For C positive. How am I missing something?
N sufficient large or something?
And sufficient, and bigger than 100, yeah, or something like that. Yes. So if I want to write it to satisfy you, let's write this. Yeah. No. I understand. Again, I say that I throw away a few things, but if you want to see it, then. And similarly here, if this was the TNC tilde, then the same limit is 1. But what changes is the minus. Okay? Is that good?
They're limsurs, right?
Excuse me?
The inner one is probably a limsur. Right.
Wait, let me. Okay? Yeah, and so I just want to go back to the limit profile thing, which says that this cutoff is about the limits to infinity. The limit profile is actually giving you the whole function, so it's a much more powerful thing to know. Okay, so any other comments about the theorems or the models? I did want to make a connection that, this is an interchange process, so it is wonderful to give this talk after Door's talk. You have already familiarized yourself a little bit with card shuffling yesterday, but this is a finite setup. Okay, so let's talk a little bit about how to prove these type of things. And I have to apologize to Diaconis and Shahshahani. I'm oversimplifying again. Not saying anything wrong, however. The main idea in both of these theorems is to go through the L2 norm, so do Cauchy-Schwarz, and use eigenvectors and eigenvalues of this transition matrix. So let's talk a little bit about it. In this wonderful setup where, in both cases, P is symmetric, then we have the spectral gap. So we have real eigenvalues. So for whomever knows the fact that we have a generating set of the symmetric group and the fact that the identity can happen with positive probability, give us the fact that the biggest eigenvalue is 1, second biggest is strictly less than 1, and the smallest one is strictly bigger than -1. That's important. So these are the eigenvalues. They're all real because we're symmetric, are the eigenvalues. Of P. We also have an orthonormal eigenbasis, but luckily enough, we don't care about it in this setup. So to bound the total variation distance, what we do is Cauchy-Schwarz and go through the L2 norm, which in this wonderful setup turns out to be equal to the sum of the eigenvalues to the 2t, excluding the very first one. Okay, so, I'm saying that this is specific to these specific walks because otherwise you need the eigenfunctions as well, but here we don't. So now the question is, how do we find these eigenvalues and how do we analyze them? And this is where representation theory comes. So to find the eigenvalues, this is again due to Diaconis and Shahshahani. It turns out that whenever you're walking on a group like here, the transition matrix is similar to the following Fourier decomposition matrix. I'll explain in a minute what this is. So the row i's are group homomorphisms from G to GLN, or GLD, And they are what is called the irreducible representations of Sn. So we know a bunch of things about them. You don't need to worry about it right now, but p hat at such a row is the Fourier transform. So you really average, if I start at the identity and I land at G, the probability of that happening, we add over all G, the value at rho G. Okay, so that's a really a non-abelian type of Fourier analysis statement. And so let's erase this. Actually, let's just. So in the case of random transpositions, things are very nice. Because these Fourier transforms, whatever they are, you might not know representation theory, that's fine. But these things turn out to be multiples of the identity. So okay, so that's a consequence of Shor's lemma. So whenever actually you have a conjugacy class walk, so transpositions form a conjugacy class, and whenever you put a uniform measure in them, then you get, this is how you diagonalize things. Okay, so, but once you go and you twist the measure, I'm still shuffling with transpositions, but transpositions get different weights now, then you cannot have this beautiful behavior anymore. Just to say one more thing, perhaps to advertise representation theory a little bit, is that now if you take traces here, just to explain at least what's happening, the right-hand side becomes the eigenvalue times the dimension of the matrix. And the right-hand side, if we go to the formula over there, becomes 1 over n. That's the probability of staying fixed. Times the character, times the weight, times the character, plus a weight times the character at the transposition, because all transpositions have the same trace value in these representation things. That's another special thing about conjugacy classes. So this is how someone would compute, I forgot the d rho here. I'm taking traces. This is how someone will compute the eigenvalues. And these things here were wonderfully understood for transpositions, and this is how Diaconis and Shahshahani got the eigenvalues and then did the analysis. Okay, this is as crazy as it will go for representation theory. We're back to more basic linear algebra now. Because as I said, let's write down their formula before I move to bias transpositions. Their formula is given by the following. So these rows, the irreducible representations, are indexed by partitions of n. So what is a partition of n? Let's say all the way to a finite. So partitions are vectors whose coordinates add up to n, and they're decreasing integer coordinates. And we like to draw them in diagrams. So, for example, if we have 3 to 1 to be a partition of 6, we like to write this as 3 boxes, 2 boxes, and 1 box. And soon we will be filling these boxes with numbers. So the eigenvalues for random transpositions if I remember correctly, are given by this formula. I'm interchange capital and small m, that's not good. What is this diagonal index that I write over there? The diagonal index is you look at your diagram and you put coordinates, coordinate 1, coordinate 2, coordinate 3, 1, 2, 3. So these boxes have coordinate. This is the 1, 2 box, for example, and so on. So for each box, you subtract the coordinate, j minus I coordinate, and you add all those coordinates, differences of coordinates for every box in your shape. So here, this is the 1, 1 box. The difference is 0. Similarly here, the 2, 2 box. Here it's 2 minus 1 is 1, 3 minus 1 is 2, and then symmetrically, I mean, I chose something very symmetric. So if you add all those numbers, this specific thing contributes 0. Just to understand the statistic. And this is a statistic that will appear on bias transpositions now too. Okay, so this very elegant story was for random transpositions. Now for bias transpositions, let me give you the formula and then let me tell you a heuristic at least as to why this is true.
Can I ask a question?
Absolutely.
When we take T large, are we only interested in the sub-leading eigenvalue, or do we care about all of them?
We care about, so you're absolutely right. There will be some main terms that I'll give you at the end that basically have very, very large first row in this two models. But at the end, you need to control the entire sum. For random transposition, and what happens is that in the leading terms, the biggest eigenvalues have smaller multiplicities. The smaller eigenvalues will have huge multiplicities. So you need to make sure that that doesn't cause any issue. It will not. It will not cause any issue, but you have to make sure. And for random transpositions, it's very neatly done by Diaconis and Shahshahani. In our case, it was a pain to do the analysis. So, and this is why our window is a little bit off. It is because the small eigenvalues with the big multiplicities are still causing us a trouble, and we need to get smarter about it and kill this term. Thank you for the question. It's a great one. And I will get back to it at the end in terms of the heuristics. I'm doing well in time, I think. Okay, so the eigenvalues that we found for bias transpositions now are of the following form. So I'll check it in a minute to make sure I'm not making a mistake. Okay, let's see what is that. So lambda is a partition of capital N, so the whole deck. Mu is a partition of little n. Mu is a partition of little n as well. We see the diagonal indices appearing here of these three partitions. We see different weights appearing there, depending on A and B. This is the probability of being fixed. And if A is equal to B, we should be retrieving this formula, which we do. These two terms disappear, and then A equals B means they're both equal to 1. So if you do the math, hopefully you get the same thing. Now, this comes with multiplicities that some of them will be 0, meaning that. Let's write down what the multiplicities are. I didn't say anything about multiplicities over there, although the Fourier transform thing implies the multiplicities. Multiplicities. So I'll define things in a moment. That's the dimension of the lambda representation times the dimension of the mu representation times the dimension of the nu representation. I'll explain this combinatorially without any representation things at all. Times the Littlewood-Richardson coefficient of these three guys. So yeah, this now gets more combinatorial, where Okay, let's write the statement, then we can explain these things. Okay. So let's explain what these things are, at least define them. When you have your diagram, and then d lambda is the number of ways to fill this diagram, to fill the boxes with numbers 1 through n, so that you get increasing rows and increasing columns. And then rows also increase. So for example, we have 5 things. You can go 1, 2, 3, 4, 5. This is increasing. But there are many ways of doing this, and this is what this d lambda captures. So you do that for lambda, the partition of the big N. You do that for mu and nu. These are different shapes. And then there is this mysterious thing. This is way more complicated, but similar type of combinatorial description will give us the following. So for this thing to be non-zero, you need mu and nu to live inside lambda. They're sub-boxes, they're sub-diagrams. And what you do is that you take lambda minus mu, that's a skew diagram. So let's say mu is just this thing. So in this example, if we remove these 3 boxes, we get a skew diagram. We put dots for everything that is missing. You just get this. Okay, these 2 boxes, just to explain what this thing means. Remove mu from lambda. And now, in whatever you have left, you want to fill, count the ways. So this counts the ways of filling these boxes, of filling this skew diagram with, not 1 through n now, you need with, remember this is a vector nu1, nu2, nu-l, so you fill it with nu1 ones, nu2 twos, blah, 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 nu-k k's. And the restriction, perhaps I shouldn't write it, the restriction is that you want to weakly increase in rows, strictly increase in columns, and if you take the word that occurs, the word means that you concatenate the reverse rows. You need this to satisfy the ballot property, meaning that I should appear at least as many times as I plus 1. I don't want to write it, but I'm just telling you this is a very combinatorial object that appears a lot in algebraic geometry, actually. So we have a description for this C lambda mu nu's. In fact, there are many descriptions, some geometric, some combinatorial, but in this language, it's a filling with certain properties. And it's what makes our life hard. As I told you, the multiplicities is what we need to bound for the smaller eigenvalues, and this guy, we need to understand it better. And algebraic geometers do. We just have to keep up with them to get the correct window. I want to give a sketch, linear algebra theoretic sketch of this thing. Why do we get something like this? And we don't have to worry that much about the multiplicities anymore. I'll do it here so that we're right next to the formula. And what happens is that one way to think of the transition matrix, and hopefully I'll do it correctly, is as an element of the group algebra. Again, name dropping, it's very easy. So we could think of the following thing. So we start adding transpositions, whatever that means, and assign their weight. So if A and B, say if A is from the top half and B is from the bottom half, for example, the probability of doing this transposition is, let's say, A, B over N times 2, because we don't know which hand touched which card. What if we were to, so this is a sketch of the proof. Sketch. What if we were to do top and bottom, so top and top? So now this happens, I don't remember if I, oh, and A is a bad, A and B are bad here. X, Y, yeah, these are my weights, right? There are more letters in the alphabet. Okay, so here it is something like this. It doesn't, the weights don't matter. I mean, hopefully I can do this correctly. But what matters is that this is a copy of random transpositions times some weight. So sometimes some rescaling. So this is C1 times random transpositions on N cards. This is another copy of random transpositions. So C2 times random transpositions on N cards again. And this thing is more complicated, but if we drop, to understand this, we do this trick. That if we drop all weights, or put the same weights to everything, then we get random transpositions on the big thing. Top, top. This was bottom. Top, top. Okay. Then this sum times the correct weight is exactly random transpositions on N cards. Okay, so that's just the trick. And so what you'll say? Well, what happens is that these things basically commute. And so if I diagonalize, they're simultaneously diagonalizable. So we know how to diagonalize this because of Diaconis and Shahshahani. We know how to diagonalize this because of Diaconis and Shahshahani. If we solve for this, it's this minus this minus this, then we know how to diagonalize this because of subtracting things. Now, this is a heuristic, meaning that we need to do it very carefully. We need to subtract the correct eigenvalues from the correct eigenvalues. So we need to stick to the same representation, so on. This is just an idea of what's happening. And if one wants to do this very, very carefully, what we actually do is that we take the representation that we care for, and we look at it as an SN cross SN representation. Okay, this is just one line for people who know what's happening. And the way that this would decompose in terms of irreducible representations of SN cross SN is exactly what you expect according to this, which is Littlewood-Richardson coefficients, and then an S mu cross S nu. These are spec modules. So here it says lambda, the irreducible representation. That's the decomposition. If you take an irreducible representation of S capital N and you restrict it to this group, this is what you get. And this is how it is done strictly, in case someone wants to know something extra. But this heuristic should be understandable by everyone, I hope. And if you really take the eigenvalues correctly, you will retrieve exactly this. And the correct normalization constants, you will retrieve the formula I gave you this. So the heuristic, even that just gives you the formula. Okay, so this is how we diagonalize. I do want to say one thing about the analysis. But before doing that, to finish the conversation about diagonalizing, I want to say that the cases where we can diagonalize card shuffles, I told you, random transpositions, then star transpositions work by flat-toed Lisko whales, random to random Diker-Sayola, and one-sided transpositions, again, based on the previous work of Diker and Sayola. And that's it. So 4 examples. 4 examples is how much we have. So even though this sounds like a very strong technique, getting our hands on all of the eigenvalues is still difficult. And when it happens, you embrace the beauty.
Is it then similarlistic for your work that you can do also 3 probabilities if you divide the deck into 3?
So what you need, according to the heuristic, is the decomposition. So to understand exactly, I was talking to Lauren Williams about this, and she was like, do it inductively. So we're getting there. I have to learn a few things, but yes. And then the other thing is that we did this trick of solving in terms of things I know. This will get a little more complicated as you go into more packs, right? Yeah. But I don't see right now what the difficulty is because it's a technical difficulty. So yes. Any other questions? Okay, so I made my point that we really cannot diagonalize much. So let me just show you a little bit of, no, I want to keep this. Just to show you the main terms. So whenever we want to understand, when we get our hands on eigenvalues and we're like, these are, n factorial eigenvalues, you're like, well, where do I start from? Who will give me what? You always start with the following shape. So again, heuristic, but in the case of transpositions, this is connected to the Aldous conjecture, which is that you will see the spectral gap inside the random walk in the interchange process. So this guy, whatever it does, this one box means that I only care for one card. That's what this means. Everything else is together, so I cannot distinguish them anymore, so only this guy. So the shape here is 2n minus 1, 1. And the lemma for bounding the eigenvalues, and I'm not going to prove that, is that whenever we have, not only this, but whenever we have a partition of 2n, and lambda 1 can be written as 2n minus j, then let's call this the eigenvalue with respect to lambda, mu, and nu that you care for is bounded by this type of thing. And we also have a lower bound. I will not care about the lower bound. The formula, of course, it matters in the analysis, but just to give you an idea of what's happening, this is a monotonicity type of statement saying that the maximum eigenvalue will be attained in 2n minus j. So taking lambda to be 2n minus jj, taking mu to be the trivial representation, and u to be j times. So that's why you don't see mu and nu at all. We killed mu and nu, and you only have something as a function of j and the weights. Okay, so in the case of this guy, j is just equal 1. When we come here, so this term doesn't even exist, and the eigenvalue is, the upper bound that we have is this. Let's kill all multiplicities, so we don't care about Littlewood-Richardson coefficients for this computation. There are roughly 2n squared of them, upper bound, to the 2t. So this is what's going to give us the cutoff time now, because to kill this guy, you need to take t to be 1/2 to kill this 2, n over b, and then log of this thing. So the 2 will come out. And this is how you get 1/2 capital N B log 2n, which is capital N. If you do this, this turns this into 1 over E, or it becomes less or equal than 1 over E. And so if you add, now I'll only add C and steps, then you get the C over here. OK, it shouldn't be N, it should be this thing. But I'm just telling you, this is how you determine where does the cutoff time comes. You go to the n-1 dimensional representation. You look carefully at the multiplicities. Here, it shows that it doesn't matter. I took the biggest guy, I put all of the weight there, and this is what I got. OK? And this is exactly what the theorem advertised as the upper bound. And on the last 3 minutes, all I'll say is that, I mean, even though I'm very satisfied this was resolved, and I was thinking of this question for many years, and the reason why I suggested this problem to Alan when he was an undergrad at Princeton was that I wanted us to understand the Diker and Sayola technique for random to random, whomever has heard these words. So there is a hidden technique there that did not work at the end of the day for this shuffle. But there are other shuffles that Samir and I are looking at right now, and we're trying to come up with a new technique. And hopefully that will work. And this is one of the reasons why I'm looking at this type of card shuffles, to sharpen the techniques. OK, I'll stop there. Thank you so much for your attention.